In this video here, we're going to take a look at the classical and practical traveling salesman problems. Now, there are two variations of the traveling salesman problem. And before we discuss the difference between the classical and practical traveling salesman problems, there is some terminology that we do need to be familiar with. So to begin with then, a walk in a network is a finite sequence of edges such that the end vertex of one edge is the start vertex of the next. And then a walk which visits every vertex returning to its starting vertex is what we call a tour. Now, the traveling salesman problem involves finding a tour of minimum total weight. And it has to be said here then that there is no efficient algorithm for solving this problem. So in practice then, what we do here is we find an upper bound and a lower bound for the solution, and we use these to trap the optimal solution. So if our upper and lower bounds are close, then a solution between the two may be acceptable. And the aim here then is to find upper bounds and select the smallest. We then find lower bounds and select the largest, with the aim being to trap the optimal solution in as narrow an interval as possible. So let's just quickly discuss then the difference here between the two variations of the traveling salesman problem. So let's just take a quick look here then at the difference between the two variations of the traveling salesman problem. Now, in the classical problem, each vertex must be visited exactly once before returning to the start. And in the practical problem, each vertex must be visited at least once before returning to the start. So as you can see then, it's not a massive difference, but it is an important difference. Okay, so just please do be aware of this difference here. And if we convert the network into a complete network of least distances, the classical and practical traveling salesman problems are equivalent. They just become the same problem. And to create a complete network of least distances, you ensure that the triangle inequality holds for all triangles in the network. Now, in practice, this is somewhat redundant, and you'll see that as I work through the practice question a little bit later on. I don't really think that this is necessary, but if you do find this helpful, then that's great. Please do use it. But like I said, somewhat redundant, but it is worth being aware of. Okay? So the triangle inequality states then that the longest side of any triangle must be less than or equal to the sum of the two shorter sides. Now, if we have a network where the triangle inequality does not hold in one or more triangles, all we simply do then is replace the longest arc in those triangles by the sum of the two smaller ones. What this does then is this creates a network which shows the shortest distances. So to finish with then, let's just quickly discuss here what is known as a table of least distances. And then to finish with here, let's just quickly discuss a table of least distances. Now, the distance matrix for a complete network of least distances is what we call a table of least distances, right? It's not a particularly creative name, but there you go. And it shows the shortest path between any 2 points in the network. Now, if we must find or complete a table of least distances, we can usually just do so by inspection. Now, if the question requires you to use Dijkstra's algorithm to find a shortest path, you'll be told to do so in the question. So just keep an eye out for that, right? And do be cautious then as you complete the table of least distances, as the shortest distance between a pair of vertices may not always be the direct route. So do check carefully for non-direct shorter routes. And with all that in mind then, let's just work through a practice question together. So for this question then, all we want to do here is complete the table of least distances for the network below. That's this network here, right? We've also got our table. And the first thing that I can see then for this network here is we have no loops. Now, why is that important? Well, what that tells me here straight away is we can't go from A to A, B to B, C to C, so on and so on. So the way that we represent that then on our table here is just by doing dashes along the leading diagonal. Okay? Now, what I can also see here is this network is an undirected network, and that's important. Now, why is that important? Well, if we look at the table here, once I complete this row here, what that means then is this column here will be identical. The same is true here for row B and column B, row C and column C. So in other words, the table then will be symmetric about the leading diagonal. So it just simplifies the whole process, right? So let's just get started then with A to B here. So going from A to B here, this is pretty easy to see just by inspection, but if we just think about this then, there's a couple of different ways that we can go from A to B. We can go directly from point A to point B with a distance of 10. Now, alternatively, what we can do then is go from A to D, and then from D to B and that would have a distance then of 8 plus 7, which is 15. But don't forget then, we always want the value here of least weight. So in that case then, just input 10 here as our value. Now for A to C then, so again, there's a couple of different ways that we can do this. I can go from A to B and then B to C. That would have a distance of 20. Alternatively then, we can go from A to D, D to E, and then also E to C. And that would have a distance of 8 plus 7, which is 15, plus 4, which is 19. So clearly, 19 is less than 20. So we input that into our table. Good stuff. Again, for A to D here, this should be easy enough to see just by inspection. So going from A to D here, that has a distance directly of 8. Alternatively, we can go from A to B and then B to D, but that would have a distance here of 17. So clearly, A is smaller than 17. So we input that into our table. And then for the final value here along this row, that is A to E. So what way can we do this? I can go from A to B and then B to E. That would have a distance of 16. I can also go from A to D and then D to E, and that would have a distance of 15. So clearly then, 15 here is the value of least weight here, or the value with the least weight. We input that into our table, and there we have it. So this here is the first row. And as we just mentioned a little bit earlier then, this table here is symmetric about the leading diagonal. So this value here is 10, this value here is 19, this value here is 8, and then finally, this value here is 15. Perfect. Okay. Moving on then, let's go through row B here. So B to A is complete, B to B we can't do, so for B to C then, what would that be? So going from B to C here. So I could go directly from B to C with a distance of 10. Alternatively then, what I can do here is go from B to E, and then from E to C. And that also has a distance of 10. So clearly, it doesn't matter which way we go here, the shortest value is just simply 10. Okay, input that into our table. What about B to D then? So going from B here to D. Again, easy enough to see by inspection here, that would just simply be 7, going directly from B to D here. And then finally, B to E here. So B to E, again, easy enough to see here by inspection, right? Clearly not going to be 7 and 7. It's not going to be 10 and 4. We're just going to go directly from B to E, right? With a distance of 6 here. Perfect. And now that we've completed this row here, we can now complete this column here. So we get 10. I've got a dash here because clearly I can't do that value. This value here corresponds to this value here. This value here corresponds to this value here. And then finally, this value here corresponds to this value here. Perfect. Okay, good stuff. Let's go through this row here. So, we've already completed C to A here, 19. C to B, we're already done. C to C, we can't do. So I've only got two values to consider here. C to D. So going from C here to D. What's the shortest way to do that? So I can go from C to B and then B to D. That would have a distance of 17. Alternatively then, I can go from C to E and then E to D with a distance of 11. So clearly then, 11 here is of least value. So we input that into our table. And then finally here, C to E. And again, this is easy enough to see here by inspection. That would just simply be 4. Okay, so we input 4 into our table there. What that means then is we can now complete this column here. So in that case, then what I'm going to get here is 11 and 4. Perfect. Okay. And as we can see then, we're pretty much complete here with this question. Just these two values to complete here, but clearly, with it being symmetric at the leading diagonal, once we find one of these, the other is just the same. So for D to E then, so going from D to E here, again, this is easy enough to see here, just simply by inspection. And that would just simply be 7 then, going directly from D to E. That would just give us 7 here as the least value. So we input 7 into the table. And again, because it's symmetric by the leading diagonal here, that means this value is also 7. Okay. And there we have it then. So as you can see, the process here of completing the table of least distances for a given network is pretty straightforward. Just take your time, just be very, very careful. But other than that, That's all we simply need to do there. Okay. And there we have it then. So that gives us the solution here to the one practice question for this video. And that brings us to the end then of this video here on the classical and practical traveling salesman problems.